Hey everyone, my name is Akash Vachar and I'm a site reliability engineer at LinkedIn. Today I'm going to be talking about how LinkedIn performs maintenances at scale. In today's agenda, we're going to be talking about what was the motivation behind LinkedIn creating a whole platform to do maintenances. Then what were the SRE principles that were involved and which shaped how the project went. The project itself, which served as a solution for our problem, as well as what lies ahead. So let's get into it. Now, the real motivation for this comes along once we first agree on what a maintenance even is. So for our purposes, a maintenance is going to be a planned activity on the underlying IT infrastructure for the purposes of hardware or software upkeep. What I mean by that is any kind of server upgrade or a network switch firmware upgrade, or it could be even as simple as a server disk replacement. Basically anything and everything which is required from time to time to keep the hardware or software healthy so that it can continue to serve for your services. Cool. Let's move on. So now we are well equipped to define what the problem is. The problem is that these infrastructure maintenances can really cause an impact. What I mean by that is you can plan them ahead of time. However, at the moment of actually conducting these maintenances, there is no real guarantee that they are not going to cause an impact, because in a microservice environment, services move around all the time. That leads into our second point, which is a headroom check could solve this out. However, what I mean by a headroom check is perhaps something I should explain first. So imagine if every service came with a check which you could just perform to know whether or not that service can take a given amount of impact or not in the form of particular service instances going offline. So this is very typical to imagine a server going down. Now, a server may be housing multiple services on it, and those service instances will be unavailable. If any one of those services found that particular service instance to be crucial, that will lead to impact for that particular service. So a headroom check in this particular case would have failed for that particular service, but perhaps for other services it could have passed. So it's a simple way to check whether a service allows the maintenance to proceed or not, on the basis of whether it's going to cause an impact or not on that service's availability. We're going to circle back on the headroom check. So just keep that idea floating in your head for now. And finally, one thing that we realized was that some services were not at all easy to have a deterministic answer for their headroom check. So much so that a human would be required necessarily to check multiple data points and multiple graphs before a clear signal could be given for maintenance to go or no go. This will also come along and circle back to us. So let's keep that in mind as well. Now, this is the most common aspect, which is just the more hardware you have, the more maintenance you'll have to do. As simple as that. So LinkedIn right now functions across multiple geographically distributed data centers across hundreds of thousands of servers. With such a scale, you also have thousands and thousands of network switches, and some of them are very problematic ones, such as single top of rack network switches. And performing maintenances on all these servers and all of these switches can prove to be a nightmare. I would like to especially call out the single top of rack network switches here, because they especially serve as a big problem. So for those who may not be aware, a top of the rack network switch is basically in a data center. When you have a whole rack of servers, that rack of servers typically has a network switch in that rack somewhere, typically on the top, that connects to all of the machines on that particular rack. So you typically have one or more network switches. The total number of switches determines the redundancy of how many switches do you want. So you bear a cost in redundancy, but the good part is a single switch failure does not cost you too much. However, if you are dealing with such massive data center and such massive hardware footprint, you might want to cut back on the number of switches you keep for redundancy, and which is why LinkedIn went with single top of rack network switches in some data centers as well. Now, this means there is no redundancy on network switch level. So these particular switches, when they go down, all the servers under that in that rack are pretty much network partitioned. So performing these maintenances is walking a tightrope. And if not done properly, they will cause an outage. So before we delve into what were some solutions, some ideas that came our way, we should probably revisit some of the SRE principles and how do they apply in this particular scenario. So we're going to start with embracing risk. This is easier said than done, but pretty much the core idea here is do not aim for 100% uptime because there is always a trade-off between the cost and reliability of a service. If you are gonna aim for 100% uptime, you are pretty much gonna realize that the cost increases exponentially the further you push it, further you push availability closer to 100. So ultimately, you settle with the idea of service level objectives, which are SLOs. And the flip side of the coin is error budgets. So anything that is not your SLO becomes the error budget, which is the quantity of acceptable unreliability over a period of time. So to give you a more concrete example, if you have, say, 4 nines of availability as an SLO for a particular quarter, that means 99.99% uptime for your service in that quarter. That means there is only a tolerance of 0.01% downtime, which basically converts into your error budget in time when you quantify it over 3 months. And whenever you have an outage, any outage for any reason, any purpose, it's going to eat into your error budget. And once you exhaust your error budget, at least the theory says that you should stop shipping more code and only focus on reliability. So one thing I did gloss over is that I applied error budgets purely on availability. However, they can be applied on other dimensions as well, such as latency. This is all completely governed by the business needs and how the service was written and for what purposes. And finally, from our perspective, the context of maintenances, whenever maintenances go wrong, they are going to eat into your error budget. So this will play into how a service determines what is its actual effective headroom that it can safely maintain on a regular basis. To give you more examples here, if a service is very stable and it never delves deep into its error budget, it may get away with a significant amount of headroom which it can provide for maintenances. And because it can take that extra risk. However, on the flip side, if there is a service which is very sensitive to the error budget fluctuations that may happen because of wrong maintenances, chances are that the headroom check is going to be pretty stringent for that particular service, and perhaps might even have multiple checks to prevent any unsafe execution possibilities. This is perhaps a pretty obvious one, but as an SRE, we are all always hunting for identifying and eliminating toil wherever we see it. So toil is kind of difficult to pin down, but pretty easy to spot when you're directly looking at it. So we realized that maintenance activities were actually becoming a big part of toil. In fact, before LinkedIn took to writing automation and the whole platform we're going to discuss in a moment, all of this was pretty much done by hand. So if you have a single server which requires a downtime due to a maintenance for, say, a CPU replacement, you are going to find all the services running on that machine, get all the service related on calls, and get their approvals that this machine needs to be either evacuated or just give us an approval that this machine can go down and it's not going to cause an outage for you. And then the DC tech would probably take that machine out, do whatever maintenance is required, and then put it back in and let these on calls know that, hey, the service is back, the machine is back, and you can bring your services back up as well. So with all that, it pretty much meant a lot of back and forth, a lot of coordination between humans. And you can only imagine what would happen when a single Tor network switch has to go down, because now you have a huge number of machines and a huge number of services as well. So those were usually a mess and would take up to a week to get through. So pretty much telltale signs over here were that this kind of work was scaling linearly as our hardware was growing. So once we identified that this is a big part of toil for a particular section of SREs, we pretty much realized that we need to tackle it head on, and that's when the focus was given to this particular project. And finally, what better way to eliminate toil by introducing automation in the mix. Now, automation is not there just to handle scale, but automation also affords us consistency as well as faster operation time than humans. This goes without saying that automation, when done right, can also provide a platform which can be extended for other automation to leverage and collectively unlock more value for the whole company. So with all these three principles fresh in our mind, let's talk a little bit about what was the solution that LinkedIn came up with. The solution was pretty much a platform for safely performing maintenances at scale. And given that the very first maintenance that it tackled was top of the rack upgrade, it got named single TOR switch upgrade automation, or in other words, STORU. There were three major components of STORU, which I'm going to talk about on a very high level. We're not going to go very deep, but they are impact analysis, approval management, as well as automated execution. Impact analysis is what is exactly the impact that's going to happen when a maintenance is conducted. One way to imagine this could be, imagine a maintenance as a meteor that's going to come and strike a city. Now, in that particular city, how many buildings exist? And within those buildings, how many people exist? That could be looked at as the impact analysis for that particular meteor. Similarly, for a particular network switch, let's say a single TOR network switch, which has to be upgraded, firmware upgraded, let's say, what are the machines which are under it? And beyond that, what are the actual services running on those machines as well? These are important questions, and they need to be answered before anything else is done. One final part is we need to keep this information fresh. It shouldn't really get stale, because let's say the maintenance cannot proceed right now, but it can be done, let's say, next week. We will be asking these same questions again, because within the week, services may have moved around, right? So we need a impact analysis component which does periodical refreshing of these answers as well. Now we have approval management system, which is pretty much just asking one question and one question only, which is, are all the services which are going to be impacted due to this maintenance okay with this particular maintenance going forward or not? This stems directly from the impact that is already analyzed. So if even a single service says that no, the total impact which this maintenance is going to cause will be more than the headroom that it can sustain, then the maintenance should not proceed. So we are pretty much looking for complete approvals, or otherwise the maintenance should not proceed and deemed unsafe. Now, this is pretty difficult as well, because these things can change on a minute-by-minute basis, because services move around infrastructure in a microservice environment, as we previously mentioned. So these need to be refreshed as well, the answers to this particular question. And one more thing is, we cannot rely on humans to answer this question. We need automation to answer this question. So there need to be headroom checks which are created per service and kept in some form so that they can be automatically triggered, and the thumbs up or a thumbs down can be fetched at will, basically. The final piece of the whole puzzle is automated execution. And it basically just means now we have gathered all the approvals related to the maintenance, and we are totally fine with going ahead with the actual maintenance via the DC tech, or if it's a firmware upgrade, maybe even via an automation. One thing to note here would be that there is a value in gracefully shutting down these services before we perform the maintenance, and similarly gracefully bringing them back up post the maintenance as well, because these can significantly reduce the time spent by the services in a degraded manner, in a degraded state. So that's basically automated execution. Now, we have all talked about the three major components. Let's see them in action. For our purposes, we can assume that a network switch, an SRE basically wants to do a switch upgrade, a switch firmware upgrade on a given switch in production. The very first thing you need to do is impact analysis to know how big is the impact radius for this particular maintenance. This is going to do two things. One, get me all the machines which are different host names under that switch, as well as discover all the applications which are running on those machines, which are the services W, X, Y, and Z, and multiple instances of them may be running. So they're outlined as well. The next step in the line is getting approvals for each of these services, W, X, Y, and Z. Now, one thing that I've harped on so far about is the headroom checks. And truth be told, for a lot of these services, the headroom checks are not too complicated. So what I mean by that is, imagine a service which is completely stateless and can be independently moved, instances can be moved from one machine to another. They are typically very very easy to reason with when it comes to their availability and headroom. So it could be as simple as the service suggesting that as long as 95% of my instances are up and serving requests, I'm totally fine with it. So the headroom becomes effectively 5%. So if for example, service W, if the 3 instances is less than equal to 5% of the total instances of service W, chances are service W is just fine and it can automatically just say headroom check passed. So for most of these, we call these static headroom check rules, which can be expressed statically without requiring multiple downstream application calls or in the moment calculations beyond very basic health checks. So less than equal to 5%, less than equal to 10%, less than equal to 5. We can even set a particular constant on how many instances in real number that you would like to not go beyond. And those could be your headroom as well. So this is what static headroom check would be. However, at the same time, there are services which require custom logic and custom headroom checks. So these automations, these services are created by service owners. In this case, service X and Y, they require special headroom checks. So the SRE owners for service X and Y would have created these headroom checks, and the approval management service can just reach out via REST API calls to know whether the maintenance should proceed or not. Assuming that all the headroom checks pass and it's completely safe to connect the maintenance, the next step is simply to just trigger the automated execution service. And if anything fails throughout this whole flow, only and only then you need to involve any SRE human. Otherwise, you're pretty much good to go, and you can actually queue up multiple switches, and they can all wait in their impact after their impact analysis in the approval management services hands. Where approval management service will actually tell you which of these switches are totally fine to execute at which point of time. So you can actually have another automation on top, which is a higher order automation to know schedule switches for upgrades, as well as trigger switch automated executions whenever they are found ready and all the approvals pass for them. Now let's talk a little bit about results. As soon as we created this platform, we realized the value that it added because the results were immediate. We pretty much went from the whole end-to-end maintenance for a single TOR switch taking 1 week down to less than 1 hour. These were huge time savings, as well as this also meant less human error. Finally, it also enabled higher order automations for fleet upgrades. I just touched upon it briefly a little before, but a good platform, a good stable platform which does one thing but does it well is pretty much an open road for opportunity. So what's next? Pretty much automated OS upgrades. What I mean by that is LinkedIn would like to have the ability to whenever there's an OS security patch, let's say, those kind of situations are where you would like to actually roll out that particular patch as OS upgrade to all of your fleet in a time-bound manner, because your trust and the brand value of a company is at stake. So we are not there yet. However, this is pretty much in the works right now. Secondly, server maintenances, which I did allude to initially when we talked about the problem, was these are a bit easier than switch maintenances. However, they're completely onboarded to Storio now, and they've become a breeze, because most of the time the automated approval serves for the data center technicians, and they do not need to reach out to humans, which is an awesome type saver for them, and they're able to perform much more maintenances due to this. With all that said, thank you so much. This is my LinkedIn profile if you have more queries and questions. And I hope you guys learned something new. Thank you.